Wojtaszek.
Yes.
Thank you. So he's going to talk about the Nazi Roman Space Telescope, which is going to be going up. Eliza is a Principal Analyst with the Space Telescope Science Institute in Baltimore, IT Liaison to the Roman Mission Office. By the way, the Nancy Grace Roman Space Telescope is another telescope named after a woman, Vera Rubin Telescope, and she discovered, or largely responsible for finding dark matter in the universe. Eliza oversees IT infrastructure, technologies, and processes supporting the Roman mission. Before this role, she served as IT branch manager, many things, Slack, Bot, Confluence, and over 900 STScI staff members, focus on architecture and modeling of complex systems and model-based system engineering and visual analytics. She has a bachelor's degree in electrical engineering and a master's degree in electrical and computing engineering from University of Michigan, Ann Arbor. Please welcome. Whoa. So I think if you want to ask a question during, it's okay, right?
Yes.
But
absolutely.
wait for the microphone to be brought to you because it's being recorded. It'll be on YouTube afterwards. Or I'll repeat the question if it's a short one. Okay, welcome, Eliza. Thank you.
Thank you very much. Thank you. Good morning. I would like to thank my friends Barbara and Dave Ockerson and Michael Albro for inviting me to this talk. I really look forward to sharing with you my passion. And that is all about the upcoming launch of Roman telescope.
Please use the microphone. Send it for you.
Okay. Really? Okay. So, we have some technical setups to do. So, I am on detail to Roman mission full-time. I support them with technology research and technology support. And they are a really wonderful team, scientists and engineers. And I mentioned to them that I was invited to this talk, and the scientists flooded me with their papers and presentations. So it's about 200 slides. And I have here, I dwindled down to 100 slides, but it's just, I went for a whole week looking at the slides and looking at what are we discovering. And especially in these difficult times, being in the universe is really, makes you feel good because you trying to understand all the phenomena that are there. So I have a lot of slides, but I'll just hit the main slides, and then the slides are here, so you can go back and review them. Because I have in my slides, I have provided the URL or website address to OPO, which is our Office of Public Outreach, which has fantastic program in public lectures, free public lectures, which explain all the phenomena, and they also have a lot of as the images come from Hubble and recently from James Webb, they provide visualizations. So that's a topic in itself. It's fantastic. They paint the picture of what it is in the different wavelength, what they see, and explain the phenomena. So I'll give you an example later on. All right, let's go to the next slide. So I work for Space Telescope Science Institute. Let me see, make sure I can advance it here. Okay, hang on one second. I have a little bit different setup than I have Okay, just a minute. Yeah, you see it, but I have to have it here because I don't see it there. Okay, so the space. Okay, yeah. The Space Telescope Science Institute is 800 people. It's a small institute consisting of few scientists in astronomy, as well as functionally they work on programs such as NASA programs as part of a contractor. So they are famous for Hubble telescope, which has been still working after 30 years. James Webb, which was launched in December 2021. And also MAST archives, where are archives for about 20 different telescopes and other probes of the universe, so that scientists can come free of charge, can come and basically use the data for the hypothesis testing. All right, we also have, as I mentioned, the Office of Public Outreach, which does phenomenal job, and I really encourage you to go, and the slides have the link, and experience the joy of exploring the universe. We just got last year a new director. She is Jennifer Lotz. She is a very accomplished astronomer. I get a feedback here. As you can see, the research topics, galaxy evolution, galaxy mergers, and she's also looking at long-term technologies, which I'm very happy about, supporting the Space Telescope Institute. So far, every mission from Hubble, James Webb, builds on itself. So they are similar software. We provide software to the telescope. So software is adjusted. But one of the ideas that we have is introducing model-based system engineering, which is basically a digital clone of our software, so we can have a simulation in-house, and we can also try different many uses for it, but basically when you test it, you can do much more efficient tests because you have a child of the thing that is up there in the space. So we're working on that. This is one of the NASA initiatives, digital, basically the new age of NASA, where they want to have virtual platforms for their telescope. So let me go to the next slides. My talk is in, okay. 3 parts. One is Roman, that's mainly what I will be talking on because I am embedded in it, but I also brought some latest images from JWST. And the beauty about those images is that they are combined with the Hubble images. So, and Hubble, they are in different wavelength. Hubble is visual, the James Webb is in IR. I'll explain everything. So when you put together, you see things that you wouldn't be able to see otherwise. Yes? Yeah, I have the slides. Hang on. Yes. And then, of course, the next telescope, which all the scientists are excited about, which is Habitable World Observatory. the planning is right now going on in NASA, basically trying to find planets that are like ours that may have the life. And okay, so all right, so a few things that I collected that help me understand the scientists. Here's some concepts. What we talk about is what is astronomy, and it's basically we're looking at the universe, which you see. Sorry, I have to. Right? Okay, so this is the depiction of where the summary slides, which I really like because it tells you what those astronomers are thinking about, and they're talking about the universe, which is on the left side. On the left side, the figure is the Big Bang, and then the universe is expanding, and so we are probing closer and closer to the Big Bang. And also on the right side is the depiction of what astronomers are studying with those telescopes. Sun-like stars in outside our galaxy, red giants, planetary nebulas, where stars are born, and basically intense combination of gas, star-forming nebulas, massive stars, supernovas, exploding stars, and red supergiants. So we'll go through some examples of that. And the other slide that I put together, because that helped me also understand, is astronomers think about light time. Okay, so it's light travels in the space, and so just for comparison, as you can see here, that from Sun to Earth, they talk about 8.3 light minutes. So here's 1 light minute is 11 million miles. So from Sun to Earth, 8.3 minutes. And then on the right is, they talk light years. So nearest exoplanet, Proxima, which we have been studying, is 4.25 light years away. So these are absolutely blowing your mind if you're not embedded in it. But those are so going back just to this slide, if you look at that slide, we're talking about the distance of Big Bang of 13.7 billion years from the time that the Big Bang to the current time. So those are the totally different mathematics, right? Okay, so here's our Milky Way galaxy. How big is space? It's 100,000 light years, so it's a huge, the galaxy. And Milky Way galaxy, we know that there are 4,323 solar systems, okay? And there are 5,785 confirmed planets, okay? The next slide that I have is a periodic table of showing you as astronomers examine what's happening. The universe is in constant change, and so this next slide, yes. Okay, sorry. So this is periodic table. What I really like about it on the bottom here, you have certain events that are happening in the universe. So for example, in green, there's exploding massive star. And that correlates to what elements you will find, and they are finding after that explosion. Okay, so exploding white dwarf is a blue, and you can see which elements. Everything else is the universe mostly composed of hydrogen and helium, right? There's also some oxygen and carbon, but all the other metals, and they are called metals, are the result of those events. So it really helps put a framework for what the scientists are doing and what are they examining. All right, you may want to ask, who was Nancy Grace Roman? She was famous. She was the mother of Hubble telescope. She was one of the first employee of NASA. She became the chief of astronomy at NASA. She was a brilliant communicator. She was able to convince Congress to fund the Hubble. That's why she's called the mother of Hubble. And so this next Roman telescope is dedicated to her. All right?
Is she still living?
No. No, she isn't. Yes, please. Oh, is she still alive? No, she is not. She passed away. But if you go on Google and you go on NASA website, they have a whole CV of her. And yes, yes, please.
Was she aware, she lived long enough to be aware that this was named after her?
No, no.
Could you repeat the question?
No, she wasn't alive when we changed the name to Nancy Roman. It used to be called WFY, yeah. Yeah. All right, so let's go to Roman, right? Okay. Here's characteristics, and I'll go through this. This is engineering, but the mission life is 5 years, plus or minus. That's how Hubble was supposed to be. In 30 years, it's still going. So the orbit that it is on is 1.5 million kilometers away from Earth, and that's called Lagrangian orbit. That's where there is a balance of gravitational forces, and you don't have to adjust the trajectory as much as in other orbits. So that space the fuel. So there's no hope if we were very concerned about with James Webb, because James Webb is at that Lagrange point. Also, we were very concerned about fuel, because you cannot send anything there unless later on maybe robotics to refuel if you run out. But the launch was very good with James Webb, and we hope this is going to be the same thing with Roman. Observatory, it has primary mirror, which is about the size of Hubble. It has 2 instruments, one which is wide field instrument, and the other one, which is still proof of concept, coronagraph. It comes from JPL, Jet Propulsion Laboratory. And it has, I'll talk a little bit about it later. And of course the bus with the download link is 250 to 500 megabits per second and 11 terabits per day. That's what it is able to support. The ground stations, the same as James Webb. We have a series of ground-based stations that keep track. And operation is Goddard Space Flight Center in Maryland, which is Mission Operations Center, MOC. The STScI has SOC, which is Science Operations Center, and IPAC is JPL has a Science Support Center. So that's how it is divided, okay? Yes, please. It has not been launched. When will it be launched? It is, okay, we hope it'll be launched by end of 2026, but the date that we report, the NASA report, is March 2027. So we are still in putting the telescope together. Yes? All right, so let's go to the next slides. And the next slide tells you who is who, right? I have to. All right, so as I mentioned, NASA is a manager. Jet Propulsion Lab has SSC. They also provide the coronagraph instrument. It's not the coronagraph has not been around. They have been around, that instrument, but they have improved the optics of the internal optics, and that's why it is on proof of principle. There is also a very active science team coming from scientists from various institutions and all over the world. And I'll talk about this. And we have industrial partners who are responsible for mechanical parts of the Roman. So Ball Aerospace, L3 Harris, and Teledyne. So this is the team. Okay, so let me go to the next slides. All right, and here is the answer to official answer to the question when, so Roman is on track to launch May 2027, but we hope it will be launched end of 2026. That's what our, okay. And the first call for proposals, when we launch, and before we launch the telescope, we have a system for proposals, so astronomers can, and teams of astronomers can propose time on the telescope, and so this is going to go out in fall 2025. All right, yes, please.
Are you saying that these are proposals for what you wanted to do once it's been launched?
Yes, the time on the, so are those proposals for the, what the scientist wants to do, or group of scientists? Yes. So they get time on the telescope, and that's their exclusive time because they work on, they have graduate students, you know, they work on the, contracts, they have hypotheses, and so, but this is going to be a little bit different, and I'll explain later on why, but there will be a proposal like this. So here's the Roman, the primary mirror, but what is different about Roman is that it has 18 detectors. Next slide. You know, it's hard to do this. So it has 18 detectors. They are 4K by 4K pixels. They are about $1 million each. They're about size of, yes, it's state-of-the-art detectors because that's what you have to have. And the mirror, primary mirror, is the size of Hubble, very much. But those, but Hubble had only one detector. In here you have 18, and they are special detectors. So go here. All right, so this is comparison Roman to James Webb. So James Webb has a much bigger mirror and the different wavelength also. And I'll show you the wavelengths, all three. So Roman has IR wavelength from 0.5 to 2.3 microns. And GWS3 has two cameras. Actually, it has 4 cameras, but 2 cameras in IR in different wavelength. So next one, let me show you this slide, it helps, yeah. So this slide shows the field of view of Roman. So as you can see, and on the bottom there, the field of view of Webb, James Webb, and field of view of Hubble. You can see the difference, right? So Roman is a survey telescope, okay? So that's why you have those 18 detectors. And so mirrors here on the top are very similar to Hubble. James Webb is bigger mirror, but James Webb has a couple of detectors. Hubble has one, and Roman has 18, those powerful detectors. This is what is needed for the job of survey, right? It'll be able to scan the sky 1,000 times faster than Hubble or James Webb. So in the bottom here is the wavelength. So the wavelength on the left side is UV, ultraviolet, then we have visible, and then we have IR. So Roman is all in the IR. The Hubble is in a little bit, as you can see, that's the bottom one, the first one. Hubble is in UV and also in visible light, and a little bit in IR. So we like it because you can see different phenomena at different wavelengths, right? And so you can really understand what's behind. Roman has narrower signature in terms of wavelength, but it is a survey, so it has a wide. This is all what Roman is, okay? Let me go here and here. So this is one of there were two instruments, right? Wide field instrument, and it has, okay, and targeted observation, obviously, is a survey. So it combines Hubble-quality imaging with a breadth of mission like Sloan Digital Sky survey. So there are other NASA missions for survey, but this is in that range. It is very unique. And the other instrument, okay, sorry. Okay, the other instrument is coronagraph, and as I mentioned, this instrument is used to detect very faint exoplanets when there is a bright star in front of that. So when the instrument looks at it, it has to block that star light, right? So that's what it shows here on the right side. It blocks it by adjusting internal filters and also flexible mirrors. So that's state-of-the-art coronagraph, okay?
Yes,
please.
Yes. Does this telescope...
Could you wait? Hang on,
is it
please.
able to-
Could you wait, please?
Oh. I just wondered if it's able to assess any qualities of those exoplanets. Does that require a different kind of instrument?
No, okay, so what's going to happen is that Roman telescope is going to work with James Webb, because James Webb is very good at going deep into an area. This is a survey, so it'll be able to identify which planets we want to study, and then James Webb will provide more data even about those planets. So that's a synergy. Yes.
I'm sorry to be annoying with the microphone, but it's because it's on YouTube. It'll be visible later, so we need the questions to be recorded as well.
Sorry.
Dan, you had a question? Hang on.
It's just that looking at the wavelengths involved, it looks to me as though the Webb telescope is able to look further out into the universe because of the infrared wavelengths. It's further into the infrared than
Yes.
this telescope.
That-
So it can look more at the origins of the universe, whereas the thing you're describing here is this helps in the search for planets.
That's right. That's
so
right.
have I
It's
got
a s-
sort of the basic differences?
Absolutely, and that's exactly right. You can have both, right? So it's a survey to be able to identify where you should be looking at, right? And then you get your instrument that is capable of multi-wavelength like Webb. That's why there's a synergy of it. So, yes. And then there will be this habitable world observatory, which will even have multi-wavelength instruments that's still in the planning stage, which will grow. I guess specs will be based on what Roman will bring us. So that's, yeah, so. The astronomers, scientists say that this is a golden age of astronomy. They've never had the tools like the telescope to be able to really have, they only could see the world through the little instrument that James Webb has, but now they're gonna see the whole and be able to hold swatches and be able to see, and yeah. So, okay, let me. I'm not, okay, so we talk most recent emphasis on exoplanets, because that's where we're trying to find, especially with the search for planets, is exoplanets. And those are planets which are outside our solar system. And most of the planets detected so far, there have been 5,000 of them only, okay? But it's not enough because they can be all gas, they can be metal, and we don't have enough of the metal to be able, obviously we cannot live on in gas, so we're looking. So exoplanets, and there are billions, and I'll show you in a little bit what the telescope is saying. So just a summary here, Roman, it's next big thing. There are reasons for the big, just remember. So Hubble-sized mirror, okay, and equivalent resolution, but has so many detectors, and it's fast, okay? So you can, well, Hubble and Webb try to do surveys, but it takes months. This thing can do it 1,000 times faster. And here is the swatch on the right, how those detectors will look at the planets. So, yeah. Yes, so let's go to the next slide, which has, okay, why we built Roman, okay, why we built telescope in Lagrangian, okay. So there is drivers, and there are three questions. What is the nature of dark energy? What is the nature of dark matter? And is there life elsewhere, right? We're trying to answer this question. But the theme for scientists right now are following: planets by the thousands, stars by the billions, galaxies by the millions and understanding some fundamental physics of dark matter, okay, and dark energy. So that's what the scientists are looking at. So where is, okay, this is at Goddard in Maryland. So as on the left side, there is hardware, the bus hardware that is ready to be populated with the instruments and electronics. And on the right side are the 18 detectors, right? So it is happening. That's why my friend went and took these pictures from STScI scientist Ori Fox, because he, everybody, and that's him standing in front, everybody wants to know what's the status, because there are many contractors have different roles, but it really is progress when you see it coming together. So, okay?
Question.
Yes, please.
How big are each detector?
Like how big the detector? He says it's a size of a palm. Yes. Yeah. It's.
You need all those solar panels because you're so far from the sun.
Right, that's right. They have on one side, that's exactly right. That's right. Don't forget, they are in Lagrangian, right? Very far away from, sorry, my computer is very jittery. Sorry, okay. So, all about Roman, right? Let's summarize. What's so special? It's infrared, right? We talked about it. It's in space at Lagrangian orbit. It has wide field of view instrument, very powerful. And another thing is that it is the only telescope that is community driven, okay? Because it cannot be a single scientist here and there, because you're going to get so much data, you're going to be absolutely amazed. We're talking about petabytes of data. Yes, please.
Is this community Earth-wide, or is this community just the United States?
No. It is worldwide. Worldwide scientists it's driven, the surveys are driven by that different communities that are together officially, scientists, and they describe their the projects, their research, and they are grounded, so they decide among themselves. I have a slide to show you. Yes, please.
I understand it's worldwide, but does that mean you've made the Goddard Space Flight Center talk to the Jet Propulsion Lab?
Sorry, you'd have to, Dan, I'm sorry to insist, but you must.
Well, I was just commenting on NASA politics that getting the Goddard Space Flight Center to talk to the Jet Propulsion Lab is very, very difficult.
Think of this as the talking stick. You have to have the talking stick to talk. Bob.
Before we move on, just quickly, on that coronagraph, you're doing a survey, so you're looking at a lot of stars at the same time, right?
Survey with a wide field, that
Yes.
other instrument. This is specific to where once you know where the exoplanets are, that's the focus of that.
Well, this is kind of what I was asking, is you can see the fluctuation of intensity of individual stars, from passings and so on. But the coronagraph goes one star at a time, or can it do multiple stars
No.
at the same time?
It's focused on one star at a time
Okay,
because
all right.
it's trying to block that star.
That particular
and
star.
to see the planet that is behind it. It's and the special planet, those exoplanets, and they come in different, they are disks, they are, solid.
So, being a survey instrument, do this star-by-star kind of coronagraph screening sounds like a process of stepping through a lot of options, which might take up some time. Is that the way it works?
That's the way it works.
Okay.
It's still in the, I'm not sure how the whole coronagraph, because it's in the proof of principle, okay? So it has to be there for 12 months to show what it can do, if it works or not, because it has those state-of-the-art internal electronics. Yes?
Sterling, hang on, Dan. Sterling has a talk.
Sterling Paulette. I have the talking stick, Dan. I was curious, how is this program actually funded? By one country, by multiple countries, the scientific organizations?
NASA. It's
Okay.
strictly NASA
Strictly
project.
NASA project. Okay, thank you.
Yes, yes.
Now,
it is
Dan, you
NASA.
may
That's
have
why
a
NASA is in
pass,
charge.
Dan.
Well, just this field of view question again.
Yes.
Webb is like looking through a straw. It's a very narrow field of view. But you can still point the straw in all sorts of directions and see anywhere in this visible, I guess, hemisphere or...
Well, in the visible light, yeah, that's
Yeah.
what Hubble did, right?
Yeah. But the field of, it doesn't mean that Webb can't see all of the universe. It just means that it's looking at it through a straw.
Yes, one small area after the other. So they try to do this survey, but it takes a long time to collect all this information. Well, this is just, you have it. Millions and billions, right?
I have another follow-up question myself about this. So James Webb, I understand, Roman, as I understand it, Lagrange point, that means it's overhead at midnight on the equator, always, right? So if you're there and you look towards the sun, you'll see the Earth transiting, you'll see the Earth in front of the sun, like a transit of the sun by the Earth. Can it look in that direction, or is it going to burn out the
I think it's looking away from the sun. The way
normally
I looked.
normally it does. My
Yes.
question is whether it can, and then it can measure the atmosphere of the Earth.
I don't think it is focused on that.
It wouldn't take
In the-
long, but
yeah,
it might burn out the sensors.
that's right.
Okay, all right, thank
That's
you.
right. When I looked at the geometry, I had a slide. I don't have it here, but I could show you the geometry of where it's supposed to be looking, and it's not supposed to be looking back there. So, yeah. So, okay, let me see. Yes, please.
One question. Sorry, one. Oh, you can hear me, I think. You can't hear me. The universe. Oh, okay. I want to speak to all the people out in the universe. My question
Very
is
much so.
a very
Thank
simple
you.
one. Is the money in place now?
Yes.
And it will stay in place? I mean, you're confident of that?
Yes.
Going forward.
Well, yeah, yes.
That's
what
obviously
was-
a political
yes,
question in a way, but
what was cut, NASA got cut on Hubble. Hubble got cut, although it's still producing the images, but support like public lectures and all the interpretation of the images as they come in. So they got cut on that.
It's great to have these questions, but I think we should hold them till the end because we've only got 15 minutes left, and I'm sure you've got 100 more slides. So,
Well, like I said, I'll leave it here at the slides, and you guys can take a look. This is my friend Ori Fox slide, and he says, what's the bottom line? So that's the Roman observes in infralight. The reason why it's up there is because it's less prone to effects of gas and dust. Okay, the IR does not travel if on the ground telescopes doesn't travel through the atmosphere. It's sensitive to high redshift targets, and redshift targets are very far away, stars and planets, and it's better for cosmology. So some of the slides. So the redshift is fundamental to the astronomers. What happens is, as our universe is expanding, and as universe stretches, it stretches the wavelength of light. And instead of being in the visible, it goes into red. That's why you have to, that's why basically we, let's see, that's why it's a redshift. It works towards the IR. And so that's what the slide is. So in a sense, you can think of it like a flip book of galaxies in time as we go and explore deeper and deeper in space. Okay, we described, I just want to show. Oh. Yeah, I'm having a hard time here. This is a flip book of time. Okay. So here is why the atmosphere is not good for IR. Here's, let me go to my side here. So here is a picture of Jupiter at one state of atmosphere, and when you have the turbulent atmosphere, you cannot see anything, right? So here are a couple slides just to remember. Invisible during the day, you cannot see the sky, and infrared not. At night, okay, visible, you can see the sky with the stars, but not infrared.
Next slide.
Next slide. Okay. Visible, right? And then in space, voila, you can see visible and you can see the infrared, right? So that's why. Okay. It's kind of nice to know these things. So Roman wide field of view, now we know that, right? In the bottom there is Hubble, so we discussed this. Highlight, so it's about 2,000 square degrees. That's the swath that it'll be. Okay, and here is comparison. That's why Roman has big data. That's why it is a big deal. Okay. Here on the top, which you don't see, here you go, sorry. Hubble, in its 30 years, collected 172 terabytes of data. Roman, over 5 years, 20 petabytes, 20,000 terabytes, 20 petabytes. That's why it's a big data telescope. So everything changed as far as engineering. Everything changed in terms of processing of data from the telescope. We have to have massively parallel processing, okay? And Roman processing is being moved all moved to the cloud, okay? So the way it works is from the telescope, it goes to the images, the data, goes to the NASA cloud where it's received, and then we get it through the cloud. It's AWS cloud. We get it for processing, and we process it, and we store the data. We also, in the cloud, have community, astronomic community. Astronomers work in AWS because so much data. You know, it's golden age, but may you be blessed with too much data. You have to have tools, totally different tools than Hubble or Webb. So astronomers are learning how to operate in the cloud. You know, in cloud you have, like AWS, you have infinite resources. What gets you is you have to pay for it. So you have to put guardrails so people don't go and spend. But basically part of Roman program is a science platform where they can sign up, any astronomers sign up, they can look at the data that is coming from the telescope, they can set up their processing pipeline. So it's all new technology that those astronomers have to learn. So that's why it's a big. So I mentioned about, let me see here. Roman is community driven, and my friend Ori Fox is liaison to that community. So they decide where the survey is. So there are so-called core surveys. You can see it. So there's galactic plane survey. There is the galactic bulge survey, high latitude wide area survey, and time domain survey. Everything in the space changes with time. So we weren't able to do it before, but now, for example, the galactic bulge survey, it basically looks at the center of our galaxy, and it observes a 2 square degree region obviously in infrared. During the survey, Roman will take a new image every 2 minutes for more than 62 days. Okay? And then repeat this process 6 times over 5 years. So can you imagine the data? You're going to have time domain data. You can see, because it's come back to the same place, you will see what happens to the planets, to all the events after 5 years, and you'll be able to do real science. So, entire community is laying out the ideas, and that's the difference between Roman. So there's a lot of coordination, obviously. Scientists have opinions, very strong opinions, and we take their opinions in the SOC, in the Science Operations Center, very seriously. They have input, so it's totally different ballgame than other telescopes, where they had a project, they could ask for time on the telescope. It's competitive. One of the John Hopkins investigator told me that he was principal investigator, and took him 3 years to get time on the telescope, on the Hubble telescope. So and he has PhD students, so astronomers, I have so much respect for them, because they must be really driven and committed. And like my friend said, right now, it's a golden age of astronomy. We'll find out things that we never knew existed. How are we doing on time? 5 minutes. So I think, obviously, I have a lot more. and you guys are very good. Once you start looking at it and the images and figuring out where these guys are coming from, it's absolutely fascinating. I couldn't put it down, So, let me see here. So here I mentioned planets by the thousands, and they have their methods. The slide talks about micro-lensing. Yes. So I go through and what technology, methodology, obviously spectroscopy. I want to show you. Let me see if I can. Let me see. Yeah. Okay. Let me see. I have some. Okay. I'm trying to get to the. I don't think we can run it, right? Because it's run on my computer.
I can trigger a video from here. Is that what you want to do?
51, yeah. I just wanted to show you the visualization that OPPO, Office of Public Research, does. So some of the, I'll just, yes, okay. Yeah. The astronomers are looking. I mean, there are some, let's see, the 53. That's very impressive. That, yeah. Tidal disruption event, yeah.
Actually, I have a suggestion. Rather than rushing through, as you've only got through half your talk, maybe you come back and give the second half of the talk another Sunday.
I'll be very happy to, if you're interested.
That would be great, because you've got so much and they're beautiful slides, and maybe you've got enough material for another talk.
Yes, definitely,
Okay.
definitely. And I'll bring some visualization, because it really, you talk, but when you see it, it's just...
Right, 2 or 3 minutes
mind.
for questions now.
Please.
Thank you. Well, let's thank her.
Yeah, thank you. You've been wonderful audience. Thank you.
Now, 2 or 3 minutes for questions, and while I pass the microphone to Bob, you've been inspired by this, so let me just make an... If you haven't been out to the Dulles Air and Space Museum and seen the IMAX of the James Webb, that's really worth going to see. And $15 to get parking, and then IMAX is maybe another $10 or something. Amazing things. So go and see that, and then in a few years we'll see the Roman telescope results there.
Yes, when you were speaking about the survey of the center of the galaxy in the infrared, what I was thinking of was you can really detect the motions of swarms of stars, if you take snapshots over a period of 5 years. So you can, I'm assuming you can get a sense of their motions, laterally as well as, redshifted way back and forth. So it's
Right.
almost like an animation of the gravitational forces
Absolutely.
around whatever, black hole we have.
Yes, that's right. Because we assume that it's stationary, and that's what we do our,
Yes.
analysis. But time domain, it's totally different dimension that will share more light.
Actually, Bob, that has been observed. The stars around the center of the galaxy, the supermassive black hole, have been observed in full orbits. That got a Nobel Prize, right? That's a ground-based telescope, but with compensation for the atmosphere of wobbling. Dan.
The risk of being put in Unitarian purgatory, I just wanted to ask the question about what you showed the last slide. The dark clouds, is that dark matter that we actually saw?
That is the dark
That is
matter.
wonderful.
Yes.
That's,
You can't see dark matter.
Yes.
You can't see dark matter, it's invisible. That was...
what were the clouds?
This was the nebula around that around this gases. Yes.
That was a
Because that's what
simulation
it
of those
is.
dark clouds, right? But not dark
Yeah.
matter. Other matter, right? Gas, whatever.
Yes, those are gas. But from gas
Okay, any other?
is
Yeah,
other metals.
okay, right?
Hi, my question is probably more the process of how this is going to be built. But I heard you say that you're going to do a proof of concept.
On
So-
coronagraph,
Right.
just a coronagraph.
Right, so my sense is you're going to, that eventually you're going to launch something. And so are you going to then have basically what you launch built and tested at some place like White Sands where you can look up, understanding that there's going to be the Earth's influence of the Earth's atmosphere, et cetera?
Absolutely.
Is that the idea of how you're going to do
Absolutely.
it? See, I think that's wonderful. Thank you.
Yes, definitely. They go through a very rigorous testing. Yes.
Yeah, that principle has been done, and we've seen exoplanets, but you're doing it for thousands of stars, right? Not
Right.
just one or two of you. Any more questions? Well, I think that was great. Your slides are amazing. I'm looking forward to you coming back and
Thank you.
doing another one. And okay, and next Sunday, second Sunday of the month, and if you have suggestions for speakers, I think I'll be doing it in December, but then we're looking for speakers for January, February, March, and so on. But we've got one already coming. Thank you.
I'll be happy.
Thank you very much.
Thank you very much. You're a wonderful audience. Thank you for your questions. Thank you.